Oh, hey, sorry, I don't mean to be rude. I'm just trying to figure out how far away my thumb is. How? Parallax.
One diopters per mankind.
Centuries ago, people thought the stars were holes in a huge crystal sphere letting through heavenly light. It wasn't clear just how big the sphere was, but it was pretty dang big. I have some sympathy for them. By eye, and for all intents and purposes, the stars are infinitely far away. If you drive down a road, you'll see nearby trees flying past you, but distant mountains move more slowly. The moon is so far, it doesn't seem to move at all compared to nearby objects. And it's easy for your brain to think it's much closer, smaller, and actually following you, which is a bit creepy. Sometimes people even think it's a UFO tailing them. Finding the distance to something really far away is tough. It's not like you can just pace off the distance. Or can you? The ancient Greeks knew the Earth was round, and there are lots of ways to figure that out. For example, ships sailing over the horizon seem to disappear from the bottom up, as you'd expect as they slip around the Earth's curve. But how big is the Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes figured it out. He knew that at the summer solstice, the sun shone directly down a well in the city of Syene at noon. He also knew that at the same time, it was not shining straight down in Alexandria, and could measure that angle. There's a legend that he paid someone to pace off the distance between the two cities, so he could find the distance between them. But more likely, he just used the numbers found by earlier surveying missions. Either way, knowing the distance and the angle, and applying a little geometry, he calculated the circumference of the Earth. His result, a little over 40,000 kilometers, is actually amazingly accurate. For the very first time, humans had determined a scale to the universe. That first step has since led to a much, much longer journey. Once you know how big the Earth is, other distances can be found. For example, when there's a lunar eclipse, the shadow of the Earth is cast on the moon. You can see the curve of the Earth's edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry, you can figure out how far away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part. His methods were sound, and they were used later by great thinkers like Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over 1,000 years before the invention of the telescope. And I think it also says a lot that these ancient thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name: the astronomical unit, or AU. Mind you, not an astronomical unit, the one. That's how fundamental it is to understanding everything. A lot of methods were attempted. Sometimes Mercury and Venus transit or cross the face of the Sun. Timing these events accurately could then be used to plug numbers into the orbital equations and get the length of an AU. Grand expeditions were sent across the globe multiple times to measure the transits, and didn't do too badly. But our atmosphere blurs the images of the planets, putting pretty big error bars on the timing measurements. The best they could do was to say the AU was 148,510,000 kilometers, plus or minus 800,000 kilometers. That's good, but not quite good enough to make astronomers happy. Finally, in the 1960s, astronomers used radio telescopes to bounce radar pulses off of Venus. Since we know the speed of light extremely accurately, the amount of time it takes for the light to get to Venus and back could be measured with amazing precision. Finally, after all these centuries, the astronomical unit was nailed down. It's now defined to be 149,597,870.7 kilometers. So there. The Earth orbits the Sun on an ellipse, so think of that as the average distance of the Earth from the Sun. Knowing this number unlocked the solar system. It's the fundamental meter stick of astronomy and the scale we use to measure everything. Having this number meant we could predict the motions of the planets, moons, comets, and asteroids. Plus, it meant we could launch our probes into space and explore these strange new worlds for ourselves, see them up close, and truly understand the nature of the solar system. And it's even better than that. Knowing the astronomical unit meant unlocking the stars. We have two eyes, and this gives us binocular vision. When you look at a nearby object, your left eye sees it at a slightly different angle than your right eye. Your brain puts these two images together, compares them, does the geometry, and gives you a sense of distance to that object. And you thought your teacher lied when she said math was useful in everyday life. We call this ability depth perception. You can see it for yourself by doing the thumb thing. As you blink one eye and then the other, your thumb appears to shift position relative to more distant objects. That shift is called parallax. The amount of shift depends on how far apart your eyes are and how far away the object is. If you know the distance between your eyes, we'll call this the baseline. Then you can apply some trigonometry and figure out how far away the object is. If the object is nearby, it shifts a lot. If it's farther away, it shifts less. It works pretty well, but it does put a limit on how far away we can reasonably sense distance with just our eyes. Stars are a bit beyond that limit. If we want to measure their distance using parallax, we need a lot bigger baseline than the few centimeters between our eyes. Once astronomers figured out that the Earth went around the Sun rather than vice versa, they realized that the Earth's orbit made a huge baseline. If we observe a star when the Earth is at one spot, then wait 6 months for the Earth to go around the Sun to the opposite side of its orbit and observe the star again, then in principle we can determine the distance to the star assuming we know the size of the Earth's orbit. That's why knowing the length of the astronomical unit is so important. The diameter of Earth's orbit is about 300 million kilometers, which makes for a tremendous baseline. Hooray! Except, oops, when stars were observed, no parallax was seen. Was heliocentrism wrong? No. It's just that stars are really and truly far away, much farther than even the size of Earth's orbit. The first star to have its parallax successfully measured was in 1838. The star was 61 Cygni, a bit of a dim bulb, but it was bright enough and close enough for astronomers to measure its shift in apparent position as the Earth orbited the Sun. 61 Cygni is about 720,000 astronomical units away. That's a soul-crushing distance, well over 100 trillion kilometers. In fact, that's so far that even the Earth's orbit is too small to be a convenient unit. Astronomers came up with another one, the light year. That's the distance light travels in a year. Light's pretty fast and covers about 10 trillion kilometers in a year. It's a huge distance, but it makes the numbers easier on our poor ape brains. That makes 61 Cygni a much more palatable 11.4 light years away. Astronomers also use another unit called a parsec. It's based on the angle a star shifts over the course of a year. A star 1 parsec away will have a parallax shift of 1 arcsecond, 1/3600th of a degree. That distance turns out to be about 3.26 light years. As a unit of distance, it's convenient for astronomers, but it's a terrible one if you're doing the Kessel Run. Sorry, Han. The nearest star to the Sun we know of, Proxima Centauri, is about 4.2 light years away. The farthest stars you can see with the naked eye are over 1,000 light years distant, but the vast majority are within 100 light years. Space-based satellites are used now to accurately find the distance to hundreds of thousands of stars. Still, this method only works for relatively nearby stars, ones that are less than about 1,000 light years away. But once we know those distances, we can use that information on more distant stars. How? Well, like gravity, the strength of light falls off with the square of the distance. If you have two stars that are the same intrinsic brightness, giving off the same amount of energy, and one is twice as far as the other, it will be 1/4 as bright. Make it 10 times farther away, it'll be 1/100th as bright. So if you know how far away the nearer one is by measuring its parallax, you just have to compare its brightness to one farther away to get its distance. You have to make sure they're the same kind of star. Some are more luminous than others. But thanks to spectroscopy, we can do just that. A star's distance is the key to nearly everything about it. Once we know how far it is, and we can measure its apparent brightness, we can figure out how luminous it is, how much light it's actually giving off. and its spectrum tells us its temperature. With those in hand, we can determine its mass and even its diameter. Once we figured out how far away stars are, we started to grasp their true physical nature. This led to even more methods of finding distances. The light given off by dying stars, exploding stars, stars that literally pulse, get brighter and dimmer over time. All of these and more can be used to figure out how many trillions of kilometers of space lie between us and them. And we see stars in other galaxies, which means we can use them to determine the actual size and scale of the universe itself. And all of this started when some ancient Greeks were curious about how big the Earth was. Curiosity can take us a great distance. Today you learned that ancient Greeks were able to find the size of the Earth, and from that the distance to and the sizes of the Moon and Sun. Once the Earth-Sun distance was found, parallax was used to find the distance to nearby stars, and that was bootstrapped using brightness to determine the distances to much farther stars.
I am in Orlando at the Kennedy Space Center Visitor Complex. This is where they launched humans to the moon and continue to do launches to this day. Behind me is the Rocket Garden and kind of visitor center, which is why there are school groups and inspirational music, but we're going to ignore all of that for today. We're going to look at orbital mechanics. These rockets behind me were originally developed to put things in orbit. So I'm going to derive the equation you need to know to keep something up in space. To do that, I need two things. First of all, I need a flip chart so I can do all of my working out in a nice orderly fashion. And secondly, I need something that's been in orbit. So welcome to Stand Up Maths. It's Chris Hadfield. Thank you for coming along. It's
3 times I've been in orbit.
It's 3 times?
3 times.
How many orbits do you do per?
I've done about 2,600 orbits or so around
wow.
the world lots of times, yep.
Okay, so 2.5 kilo orbits in. We're going to...
Orbits.
What better use of an astronaut than doing some working out? So let's do this. So do you want to set us up like the Earth with you orbiting it?
I've chosen blue.
Gone for blue.
For the blue planet.
Nice work.
Right.
And then over here, I'm going to start an equation. I'm going to go force equals mass times acceleration.
Okay.
Okay, is this the center of the...
Center of the Earth.
Okay, so let's call Earth big M mass.
Okay, great.
And then where are you in this?
I'm orbiting the world going this way. Is that going to be okay?
That seems about right.
All right,
so you orbit... This was the North Pole looking down.
North Pole looking down.
You orbit around
yeah,
with the...
that's right.
Okay.
Yeah, we go with the rotation of the Earth.
Okay.
So I'll draw myself as a dot here.
I've given you mass little m, if that's okay.
That's fine. Okay. I'm happy with little m.
Good.
All right.
And how far up are we talking here?
Well, we're about 400 kilometers above the surface, but of course we want to measure it from the center of the Earth, so we can put this whole thing right out to there. So it's the radius of the Earth plus our orbital altitude.
Okay, let's call the whole thing r.
R, okay. All right.
R squared. So I've just put in the classic gravitational force. The gravitational constant g, mass of the Earth, m, mass of Chris and everything else that's keeping you alive up there, and then this is our distance, r squared. So that gives us the force that the Earth is pulling you down, and we now need to work out, well, we know m, well, we got m, we need to know the acceleration. So to do that, let's start with the velocity you're traveling
Okay,
at.
so I'm going this way at a certain speed, a certain velocity, right?
Okay, should we call that, do you want to call that v?
Sure. Which
V1.
V1.
And it's a vector, so I'm going to put a squiggly line under there.
Okay, that's fine.
Bit of a perfectionist.
Yeah.
We're now going to have a look at you a very small moment of time in the future.
Okay, so over here somewhere, same,
you go over there
same
somewhere.
radius.
That's it.
Okay, no
That's
change
kind
in
of
radius.
the trick to staying in orbit, is this has to stay the same.
Yep, basically. And now we want another one here?
Yep.
Okay. Always parallel to the Earth's surface, and that's another V?
Let's go V2, yeah.
Okay. Okay.
And so I've done, up here I've just written that their magnitudes are the same.
Yep.
And so actually I'm just going to call it V for shorthand, because you don't want your speed to slow down.
Correct.
I guess that's kind of the definition of being in orbit.
Yep.
You're not getting lower, you're not slowing down.
We're just going like the moon, round and round and round.
Perfect. Okay, so now I'm going to add in a little angle here. This is going to be theta.
Theta, all right.
And then we've got the distance you've traveled. So you've gone from there to there.
Yep.
And that's going to be I mean,
proportionate to time.
yeah.
Yep.
So that's let's say over this tiny angle, tiny amount of t. So I'm going to put in delta t
Okay.
times whatever velocity you're moving at.
Sure.
We're now going to move these vectors, and I'm going to redraw them over here. So I'm going to borrow your red.
All
That's
right.
Okay. So I'm going to bring V1 over here and zoom in on it like that. That's our V1 vector. And then I've just moved that straight across. And this one is now on an angle down. So if I bring it over there, that's V2.
Yep.
And as you go around, I guess by the time you come all the way back to where you started, velocity is once again going perpendicular.
Yeah, at our altitude, it takes about 92 minutes to go all the way around.
Oh, 92 minutes per
92.
lap.
Yep, per lap.
And then to theta, we'll go through a full 360.
360,
So
yeah.
actually, this angle, this has just tipped your V down.
Right.
It's actually gone down by theta.
Yep, same amount. Yep.
And now that's the difference there. So I don't know if you do a lot of vectors as an astronaut.
I've done
Do you
a
have to do much math as an astronaut, or is it all?
You have to understand how it all works, but real time, you're mostly just solving the practicalities of it. Like, how do I get my spaceship from here to there? And we let the computer do the burn calculations. You have to have a sense of how it all supposed to make most of work, but we don't real time do a lot of math in public. So I'm watching and bowing to your
Well,
expertise.
no. I mean, I guess you've got a very pragmatic. You know the math, so you understand what's meant to be happening.
Yeah.
And then you trust the computers and just kind of sense check.
Yes,
As you go along. Well, in which case, you may not have done similar triangles too recently, but that's what we're going to do because we've got two triangles, both with the same angle.
Sure.
They're both isosceles because that length is equal to that length.
Yep.
As up here, that's equal to that, which means the ratio between any two matching sides should be the same. So
Sure.
the ratio here between change in velocity divided by this side, change in t times velocity equals that divided by that. So that's, well, the length of that is just v divided by the length of that is r. We've got a v down here we don't really need, so we're going to move it over there. So I'm going to multiply both sides by v, so that's now over there.
Yep.
And dv dt, rate of change of velocity, that's acceleration.
It
So
is
there we go.
indeed.
So there's our acceleration is this, which is v squared on r. So I'm going to fill that in here. So it's mass times v squared on r. This is actually just the centripetal force
Yep.
that we've worked out. So
Yep.
a lot of times when you see this taught, people just start here. They go, there's your F equals ma, and then you fill this in. That's kind of nice.
That's beautifully elegant. Yeah,
Given-
and intuitive.
It's
nice.
so good, so good.
Nice.
And given you were up on this dot, that feels appropriate. Okay, so now let's do the grand finale in brown because we can cancel some stuff out. We've got an R down there, and we've got an R, two R's over there, so we'll get rid of one of those.
Yep, multiply both sides by r. Okay.
We can get rid of an M from both sides.
Yep,
so I'm
divide
afraid
by
your
M.
mass now doesn't matter.
Right?
And I'm going to, so this side's only V squared. Oh, that's handy. So now we've got V squared equals, so I've just moved it over here, and this
Yeah.
is, these are both constants. So I'm going to put G and M over there, and then this is 1 over R.
Yep.
And that's it. That's
Beautiful.
That's our equation. So this basically shows us, if you square the velocity, you'll be able to orbit at a height r, and because this is 1 over r, it's an inverse relationship.
You know what's intriguing to me out of this is that the radius you are from the Earth determines the velocity you have to go to be staying in orbit. That's the really key and intriguing thing out of this to me. For every radius from the Earth, there is a specific speed that will hold you at that altitude.
So if you decide, I want to put either humans in a certain orbit, I want to put a satellite in a certain orbit, you then work out the specific v, which equates to that distance.
Right. And it
you're
doesn't
there.
matter what mass that thing is. It's just purely a almost geometric thing. How far away are you? That tells you how fast you have to go.
And you were in low Earth orbit?
Yeah, I didn't get above about 420 kilometers from the surface, so the radius of the Earth plus 420.
That's not bad. That's more than most people.
It is.
And the radius is like 6,000 kilometers, right?
Right,
So you're like a tiny, like
Yeah.
maybe 5%.
If you were to hold a globe and bring your eyeball down to maybe like a thumb width above, that's how
Yep.
far we were from the surface of the Earth. It seems like a long way when you're there, but it's actually still quite close.
And how fast did you have to go? What was your V for that orbit?
Well, depending which units, about 25 times the speed of sound, Mach 25. If you put it in miles an hour, about 17,500 miles an hour, about 28,000 kilometers an hour. Those numbers are so big, intuitively it's better if you go per second. So about 5 miles a second or 8 kilometers a second. In order to stay at that altitude and that orbit, 5 miles a second, 8 kilometers a second.
8 kilometers a second.
Yes.
That 8,000 meters every second.
Yeah.
That's absolutely.
Imagine if one of these rockets was right here, and 1 second later, it was 8 kilometers away. That's how
what
fast we had to be that little dot right there.
And how long does it take between when you launch and when you get to that orbit?
The rockets have to burn and accelerate you up to the right speed and the right angle. It takes somewhere just a little less than 9 minutes. From sitting here in Florida on the pad, laying on your back, to the engine shutting off and being there weightless in orbit, little under the time it takes to drink a cup of coffee.
That's absolutely incredible. So, in fact, if people want to give it a go, if you get the values for G and M, gravitational constant, mass of the Earth, and we've talked through the rough distance up you are, you can put them in and you should get out the other side roughly 8,000, which is 8,000 meters per second.
Cool, you could put in the mass for any planet and everything else still works.
Oh yeah, that's true. We've not assumed Earth. This could be absolutely anywhere.
So you can start to figure out just how fast you go around Jupiter or around the moon or whatever. Kind of neat.
Okay, tell you what, we'll put some free resources in the description below. We'll have a copy of this in case you want to recreate it. But now there's this interesting relationship between how far up you are and its inversely proportion to the speed you're traveling, which I suspect has some interesting implications for actually navigating in orbit. And I believe somewhere here is a vehicle that you've flown in orbit.
It is indeed, yeah.
All right.
Atlantis is here.
So we're going to go find that and have a chat about the implications of this. You flew on this space shuttle.
I did it my very first time to space. I was part of a crew of 5 people, and we took this vehicle, flew it up, and docked with the Russian space station Mir.
And that's not like an automated process. You don't just hit like the dock button and it all happens.
No, there's no standard orbit, Mr. Sulu. It's all sort of manual. I mean, you have primitive computers on board, a huge amount of help from Earth, but primarily flying a spaceship to dock with a space station is a manual operation, especially with something as big and ponderous as a spaceship.
So I've always known on paper, a lower orbit, higher velocity, higher orbit, less velocity. What does it actually mean if you're trying to maneuver this and you're going to connect that bit to a very specific bit on another space station?
So picture this, Matt. You have to dock that docking system to Mir. You have to do it inside a 2-minute window because you have to be over the right part of the Earth for communications.
Right.
You have to do it at exactly the right speed. Otherwise, if you come in too fast, then you'll break Mir and kill the 3 people on board. If you come in too slow, then the springs in there will bounce you off. And plus, you've got to hit it exactly in the center, because if you hit a little bit off center, the mechanism will bottom out and break. So our target was about as big as maybe a coffee saucer.
Wow.
So all those constraints, and you're flying it manually. And so an extremely difficult ballet to make all those things happen at once. And as you say, you're trying to negotiate orbital mechanics while it's happening.
So what are you doing? Are you just using the thrusters, or do you have to take into account if you go up or down, your speed's going to alter?
We try and solve that mental problem of the difference of speeds with different orbit heights by breaking your docking into phases. When you're far away, you hardly even acknowledge that the Mir is there. You're just a vehicle going around the world, and you're going to change your orbit.
Right.
And so if you're going this way and you fire the big engines to accelerate that way, then the energy is going to raise your orbit. You're going to end up in an orbit that is further from Earth. And once you get up there, you'll be sort of going at a slower speed. Like the moon takes a month to go around.
So you fire the rockets,
Yeah.
you don't speed up.
Well, you do sort of accelerate forwards, but that energy ends up, because you're going around the world, that energy sort of takes you away from the world a little higher, right?
Until everything balances back
and once
out.
you're higher and balance out, now in fact your speed is lower. It turned sort of that kinetic energy into potential energy, so now you're further away. I always remind myself, the moon is way out there. It takes a month to go around the world. And like a ball in a string, the shorter the string, the faster you have to spin it to keep the ball going. And so your string's just getting shorter and shorter. So you fire your engines and you coast to where you are. But once you see Mir, and now you fire your engines to get higher, suddenly it becomes non-intuitive, because we fire our thrusters to go this way, and we're watching intently at Mir, and we get a little closer to Mir because we move up from underneath it, and then we start drifting back.
Because you're higher than it.
Because we're higher, and now we're slower, and we're drifting back. So we're playing with our speeds as we go until we finally get close enough that we say, okay, we can no longer pay attention to orbital mechanics. Now we're just going to brute force it. We call it proximity operations, or proxops. And once you're in proxops, all you do is say, we're a little forward, we're a little aft, and just keep firing the thrusters to hone it in so that you can dock under exactly the right conditions.
So you're just compensating on the fly.
It's sort of like if you were driving two boats across a lake.
Yeah.
And once you get, and you're trying to touch maybe two parts of the boats to each other very carefully. From a distance, you know, you'll just sort of make a rough guess on where to set your throttle. And you might even just set the throttle and not even move it for a while, just catch up. Then as you get close, you're going to fine tune your throttle a little. But once you're nudging up against that other one, you're going to be all over the throttle and the steering wheel. And you won't care about the current or the wind or the surf. Yeah. You're just trying to get docked. Sort of like that.
Sometimes if I'm working out and I know I'm near the answer, it's just that's my proximity operation zone where I'm
brute force.
You just kind of, yeah, exactly. You run a simulation, you end up where you're meant to go. So excellent. Thank you so much for joining us and having a chat. I'm here in Cape Canaveral with Chris Hadfield. We're still at the Kennedy Space Center Visitor Complex, which is why there's so much inspirational music going on around us. And I mean, these are older than what you flew on, but we've got some old rockets around the place.
Yeah, right back to the very first human-capable rocket over there that Al Shepard flew on.
Absolutely incredible. And all these are basically, they're like almost all fuel.
Yeah,
these tiny bit of payload.
These are huge tanks of fuel with a little tiny payload on top.
And you were that payload.
Yeah, like a bomb with 6 seats on top. That's what a rocket is, essentially.
And most of modern rocketry came out of something called the rocket equation, which is how you can calculate how much fuel you need to get a certain mass into orbit. And the problem is, do you want to give us a spaceship here?
I'm going to draw you a spaceship.
Talk us through Spaceship 101.
So we're just going to draw a nice little spaceship here with like these ones behind us.
Oh, I love it.
With the little nozzle on the back where the engine comes out. And it's got some sort of mass, right? So we'll just call this with the mass. And inside it, it's got a bunch of fuel, but let's just call this this some amount of fuel here.
Yeah, that's tiny bit.
Tiny bit of fuel.
Not to scale.
And it's going to, once you have fired the engine, of course, that bit of mass that used to be part of the rocket is now going to be out. Where do you want that, on this one or another one?
Do you want to give us an after?
Okay, I'll give you an after then.
So this is, actually, I'll label these just because I enjoy labeling things.
Okay.
This is our before. And this is our after. And so that tiny bit of fuel is now shot out the back.
What do you want, M what?
Let's have this as DM.
DM,
for a tiny,
small d?
Yeah, small change in mass.
M, there you go.
And so I guess the mass of this is now M minus DM.
There you go.
All right. Now, before the rocket was going forward, let's do velocity in red, just because that's kind of fun. So that was our velocity before.
Yeah.
And then afterwards, it's going a little bit faster.
V plus
some D, delta
dV.
V. Right, okay.
Yeah, sure.
But that's because now this has a velocity.
Yeah.
Oh, wait, that's going to be the exhaust. Oh, because it was going V, but now it's subtract some.
Because it came out that way with some speed, but it had some of this speed, so V exhaust, sure.
Okay, the difference between what it was doing and the velocity of the exhaust comes at the back. The issue becomes, you need enough fuel to get up to orbital speed. We've done another video on that, linked below.
That's what makes how big these rockets are behind us.
Well, yeah, because then you need fuel to take the mass of the fuel that you need, and then you need fuel to take that fuel to... Right. So by the end of it, you're more fuel than payload.
For sure.
I'm now going to derive the rocket equation.
Just from these diagrams.
Just from this diagram. I'm going to look at the momentum before, and then I'm going to make it equal to the momentum of the whole system after.
That sounds fascinating. How about if I just talk about what it's like to fly a rocket ship?
Oh, okay. So I'll do the theoretical derivation.
Okay.
And you've lived it, and you talk about that. And
all right.
You can decide. You can either watch me do the working out, we'll put my audio in the left channel, or, don't know why, if you want, you can listen to Chris, who was on the rocket, talk on the right channel. So,
all right, you all good to go?
Yeah, I think I'm good to go. Okay,
all right.
So I'm going to do the momentum before was m times v. That's the definition.
So you're lying on your back inside a rocket ship, like these ones behind me. And you've been dreaming about this day for your entire life. I decided to be an astronaut about the time that Al Shepard climbed into that little Mercury redstone over there. When I was a little one, I was dreaming about it, and I decided when Neil and Buzz got into a slightly bigger version of the Saturn than that one to go to the moon, that this is what I wanted to do. And now suddenly it's the morning here at the Kennedy Space Center where you're actually going to leave Earth. You're lying on your back, and those huge engines, whether it's a Saturn V or a Mercury redstone or a space shuttle, they start to light underneath you. There's a tremendous amount of power. Hopefully no alarms go off like that one behind me right now. But you can instantly sense the enormous amount of power as they start to bend and warp your vehicle as the engines come up to you, and enough thrust to start lifting you off the surface of the Earth. There's a great vibration. It's almost like you're in the jaws of some enormous beast that is so much more powerful than you. And then, if you look out the window, suddenly your force is more than the gravity holding you down, your weight, and the launch pad starts to disappear out your window. And by the time you clear the launch pad, you're already accelerating through 100 miles an hour straight up. This force that is getting heavier and heavier, crushing you into your seat as the vehicle is going faster and faster. But you're shouldering your way through the thick air, which means there's a huge amount of vibration. You can't even focus on the instruments in front of you. What I found myself doing was grabbing onto a handrail and pulling my neck, my head, and away from the seat behind me so that my neck could soak up all the vibrations, so my eyes could cage and focus on the instruments in front of me as this vehicle is ramming itself through the speed of sound just 45 seconds after launch. And the sky goes from this beautiful Florida light blue to dark blue to black inside about a minute. In 1 minute, you're above the Concorde, faster than it ever went. After 2 minutes, your big solid rocket boosters up the side that have hauled you above the atmosphere, they're out of fuel and they explode off. And because the air is so thin up there, you have this huge pulse of flame out in front of your vehicle. But now you've got rid of those solids, and it goes from wild, crazy rough to now dead smooth, as you have just your liquid engines in the back. But now you've already escaped the Earth's atmosphere. Now you're just trying to go fast enough to stay in orbit, like we're drawing back here. And so now it's just this rocket sled ride, but absolutely beautifully smooth, like you're on some oiled cement or something, or this beautiful wild elevator that's just taking you with an acceleration you can hardly believe. And it's just inexorable, heavier and heavier and heavier, until it becomes hard to even take a breath and push your chest forward, as more and more people are piling on top of you as the G load is climbing higher and higher, because as Matt will say, F equals ma. And when your F is steady and your M's going down, your A is going up. And this vehicle is accelerating so hard eventually that the thrust from the motors, the acceleration from it, the power from it would rip the vehicle apart. And so if the computers don't do it, or we can do it by hand, you actually grab the throttles of the space shuttle and pull them back to idle, just to keep the vehicle from tearing itself in half. But finally, after somewhere a little under 9 minutes from having lied on your back, finally after a little under 9 minutes, the vehicle has gotten you to exactly the right altitude above the Earth, perfectly the right speed, you're headed exactly the right direction, and the engines shut off, and you're weightless. It's an amazing, amazing ride. We're lucky enough to do it 3 times. How'd the math go?
It was good fun.
All right.
The momentum before was m times v. That's the definition of momentum. And over here afterwards, I've got the momentum of this bit, which is dm outside of v minus the velocity of the exhaust, plus the momentum of this bit, which is m, now I'm missing dm, times, v plus dv. We're going to have to expand out all these brackets, so that's still mv on that side, dmv minus dmve plus mv plus mdv minus dmv minus dm. I can barely get the final minus dm dv in, but to be honest, that's a tiny change times a tiny change, and we don't need that at all. So I'm going to cross that out completely. I know I've been told I integrate like a physicist, but that's fine. Okay, now that can go because it equals that on both sides. We're adding dmv, we're subtracting dmv. A lot of people would like to subtract the dmv, and leaves us with these. So what have we got there? The mass times dv equals the velocity of the exhaust times dm. I'm going to get all the m's on one side, so now we've just got dv on this side equals ve times 1 over mass times dm. And now we integrate. So if we integrate both sides, that's a constant, so I can integrate there. We want to integrate from launch until we're at our final velocity. So our initial v0 is 0, and you end up at some v final. You've then got m0 when you launch, and you've got m final once you're in orbit. Okay, that's not so bad. So what I'm going to do now is integrate that onto the next sheet. So that's just v. Oh, that's easy. So that's just v, and that is from v0 is 0 to v final, and that's 1 over, oh, okay, so if you integrate 1 over m, you get the natural log of m. So that's still out the front. Here's our brackets. Natural log of m, and that is from m0 to m final. We put that in, well, that's just vf because this is 0, so that's v final equals, now we put, oh, okay, I'm not going to do log laws here, but the natural log of mf, subtract the natural log of m0, that is just the natural log, oh, that's an n, of mf on m0. So if you're not familiar with the log laws, you can look that back up again. That is still a constant, put that down the front there. Natural log means that if I move this over here, natural log means that e to the power of this, so that means m final divided by m0 equals e to the power of v final divided by v e, and that is your rocket equation, which will tell you for whatever velocity you can spit your exhaust out at, and whatever velocity you want to finally be traveling, this is the ratio of final payload to the total amount of mass that you originally started with before you launched. Thank you very much for everyone who decided to watch the mathematics on this side. I'm going to head over there and join Chris, who's probably wrapping up as we speak. Thank you everyone who was with me doing the math. So you missed, I basically...
This is the part I was just talking about here.
Oh, okay, yeah. So what I did was I equated the momentum before and after, simplified it down.
So you took just the, I see, the MV,
Yep.
and then the deltas that happen.
So this is just the exhaust, and
Yep.
this is what's left of the rocket.
Ah, okay.
A whole lot of it cancels out.
Yep.
I decided this was too small to worry about. Classic physicist. And then I put all...
this little guy here was too small?
Well, because you have a small change in mass times a small change in velocity, this
I
term
see.
is just
okay, the two of them
tiny.
multiply.
Yeah,
Gotcha.
exactly.
Yeah,
It's
okay.
gone, it's gone.
Right.
Put all the V's on one side, all the M's on the other. Integrate both from launch at V0 when you're not moving to your final velocity.
And that's the 9 minutes of launch that I just talked about?
Oh, yep. And then you've got your initial mass when everything's fully fueled. Final mass once you're in orbit.
Which is actually a big pillar of smoke and steam. You can see where all that mass
course,
went.
it's all-
It's left like a big arrow pointed at the sky here.
Oh, that's amazing. And then there you go. I did the integration, I put in some values, did a bit of rearranging. There's your ratio of payload to launch mass.
So this is mass final, which
Yep.
is whatever made it to orbit, and this is what you started out as, okay?
And then there's your final velocity, and there's your velocity of your exhaust as it comes.
We know what those two things are, right?
So what is your final velocity? What are you trying to get to?
Well, depending what orbit, but if you're getting to low Earth orbit on the space station, which is your normal destination,
Yep.
you're going to be pretty close to that. It's about 28,000 kilometers an hour, about 8 kilometers a second, 5 miles a second.
Okay, so let's do
8's an easy number.
8,000 meters per second.
Okay.
Just
sure.
because I'm SI unit kind of individual.
Yes, you are.
And the exhaust speed.
How fast
Do
does
you
the
know
stuff
that
come out
off,
the back?
off?
I don't know that. I don't know.
Oh, good. Thank goodness, because I looked it up.
Okay, good.
And it depends, because when you first launch with the solid fuel, that's coming out at roughly 2,500 meters per second, 2.5 kilometers a second.
Those are the two big solid
The two
rocket
big ones on the
boosters. Yeah,
side.
yeah.
Then once you switch to the hydrogen-oxygen mix, is that your liquid?
The liquids are hydrogen, oxygen, yeah.
And then at that point, that comes out a lot faster. That's like 4.5 kilometers a second. But on average, if you put them all together, the velocity of the exhaust is roughly 3,500, 3,400. Let's do 3.5 just to make life remotely easy. So we can
that's
now,
like the average velocity of the stuff coming out the back.
Yeah, yeah.
Okay.
I did look it up. There's slightly more mass in the hydrogen and oxygen than the solid fuel. But just to make life easy, if you average the two speeds as if they're equal mass,
Okay.
you get that. So let's work it out. So vaguely, if we were just to guess this, that's VF divided by, this should be negative, by the way. So we should put in the negative exhaust because it's going in the other direction.
Right, right.
A lot of times you will just see the rocket equation bakes in that negative up here.
Okay.
And then you put that in just as an absolute.
But this is essentially 8 over 3.5.
Yeah.
Okay.
Yeah. So it's about 2.
Yeah.
we say that?
Yeah.
So this is approximately equal to
2 and a bit. Yep.
1 over, this is 2 and a bit. So it's, an E is 2.7-ish. So, should we call that 3? It's in the worst case approximation, it's 3 to the power of 2. It's about a ninth.
Okay.
So the amount of payload divided by, as a original percentage, is about 11%, give or take. Just
11%.
over 10%, yeah.
Yeah. And that's not far off.
It's not, do you know roughly what it is, or is it?
Yeah,
you
it's
feel
in
like
the order of 10 or 15%, depending which one of these rockets you're talking about. So it works.
Pretty happy with that. I'll tell you
that.
what, we'll have some links below to this working out and some other speeds.
But 10 or 15%, that means what you're sitting on is 85 to 90% explosive. And you're just a little bit of metal and flesh on top of that. The rest of it is all just something that you would find inside a grenade or one of those classic Bugs Bunny bombs.
And that's it.
That's it. We're riding a bomb to space.
Actually, we were here recently when a solar orbiter, a spacecraft Lucy's involved with, was launched. And it was described as it exploded in all the right ways and none of the wrong ways.
Yeah, you hope that bomb explodes under a controlled set of circumstances for the time it takes to empty all of that MF out of the gas tanks.
But it means for your mass, there must be on the order of 10 times as much mass, give or take, of fuel to get you up into orbit.
Hard to believe, huh?
That's insane. The other thing, people are going to complain, we've not included gravity anywhere in this.
Right, which is always fighting the acceleration up.
Yeah. So can you recognize what that is?
That's a NASA T-38 that I flew here for many years. So that's a couple astronauts come down to the Cape. They probably got up super early in Houston this morning.
Right.
They've just flown across the Gulf of Mexico, and now they're coming out here to do some work at the place
Is
they're
that
going
the
to launch from.
standard commute vehicle
Yeah,
for NASA?
that's how you commute back and forth as an astronaut, yeah. And actually, it might be the two guys that are getting ready to launch on the SpaceX vehicle. Their names Bob and Doug.
Yep.
And one of them is a test pilot, so he'd be in the front seat.
Probably flying that
Yeah,
over.
Bob would be in the back seat.
There you go. And now planes, a lot more efficient
Yeah.
in terms of fuel, right? Because they go a lot slower.
But also, you can sort of ignore gravity when you're not going straight up. But here, gravity was always fighting us.
And I have totally ignored gravity.
Yeah.
If people want, because the two equations you need, if people want to check out gravity, is if the amount of potential energy you've got is your mass times acceleration due to gravity on Earth times the height, that's your potential energy due to gravity. Your then kinetic energy is a half mv squared. And we know V is roughly 8,000 meters per second. You know you orbit at about what? 400 kilometers, you
400
said?
kilometers,
so
yeah.
400,000 meters above the Earth. We'll have this as a free resource for teachers. If you want to download a worksheet below, you can get your students to compare these, because we only worried about this one, we ignored this one. And so you can see how close they are. spoiler alert, this one's about an order of magnitude smaller than this one. So we can totally ignore this one.
But when I went to space,
Yep.
we didn't ignore this
You
one.
didn't ignore, oh really? So you think that's quite important for, okay.
Yeah, one order of magnitude is still an important order. Yeah.
I guess if you've got to sit on it, you're a bit more worried about that.
Something else you didn't, we averaged different rockets as if it was all happening. But of course, as I described, the solid rockets only burn for 2 minutes, and then their dead
Oh, they're
weight
gone.
explodes off, and so your fundamental M changes on the way up as well. So there is some delta with that to make it more accurate.
I guess because mass is so expensive to move.
Well, you don't want to drag those empty rocket bodies if you don't need them.
They're gone.
It was a brilliant invention many generations ago. Let's not just launch everything and keep it all. Let's break it into stages. And those rockets behind us have stages as well, so you don't have to drag all the dead weight with you.
So we should have done this for each stage.
Correct.
Then change the mass and then repeat and.
But if you're just doing an average, obviously it got us in the ballpark.
Thank you.
And it shows how it works.
Yeah.
But if you actually want to precisely get to the space station, you need to get into the real fine mathematical details, of course.
Okay, I'm prepared to accept if you actually want to get to space, you've got to do a bit more detail than this.
I think it's beautiful, though, that you have shown that if you know what your final velocity is and you know how fast the stuff coming out the back is, and you know what your initial mass is, and that's all that matters.
And that's it, that's the
determines
whole
everything
line.
That is such an important and powerful equation right there. That's how astronauts fly. It's really cool. Well done.
Math. We're now going to go and have a look at something that this equation actually put into space, as well as Chris. And behind us now is something else that's been into space. It's the space shuttle Atlantis, which you flew on this.
My very first flight was on this vehicle right here on Atlantis.
And as we can see, you brought it back.
Not by myself, there were a crew,
Okay,
but yes,
team
we
effort.
brought it back, and it was reusable after landing, which was success.
But this is not light. What kind of mass are we talking?
Well, it depends if it's full of fuel or empty, but when you're coming into land, the speed you land at depends on how heavy you are, and so you have to think about it. But typically we're somewhere around 200,000 pounds. A glider weighing 200,000 pounds coming in incredibly fast, trying to touch down and land on the runway just outside here.
That's insane. And that is a lot of mass to take all the way up and bring all the way back down again.
It is.
Was that, I mean, what was the strategy behind that? And is that was that what we're doing going forward?
Well, it's all driven by purpose, right? Everything is shaped around purpose, and then you sculpt away everything else that you don't need. If you're trying to bring a huge piece of hardware up to space, and that requires crew to go outside like ants to put together and bolt and snap in and hook up, then you need a combination of big, heavy lifting capability and people all co-located together. And that's what the shuttle was. It was also designed to bring things back to Earth. Big pieces, things that are in the back, to go up to space and retrieve something and bring it home. And so you need those big wings and the big compromise design, both to lift it, to work on it, assemble it while it's up there, and to bring it back. None of those things are perfect. Compromises always pinch somewhere, but this was the greatest compromise design ever made for space flight.
Wow, and so a lot of mass, I guess, to make that all possible.
And it all takes size and volume and metal, which unfortunately has mass.
And people could live in this, right? So it's like you're taking your living quarters with you.
The longest flight was almost 3 weeks.
Oh, wow.
7 people, 3 weeks, like imagine 7 people crammed inside a camper van for 3 weeks with no bathing facilities. That's what it was like on the shuttle.
Wow. And finally, a huge thanks to Chris for coming along and chatting some mathematics and science with us.
It's all under the sun and all just math. That's all it is,
Wow,
really.
wow. And of course, NASA and the Kennedy Space Center visitor complex that we're in now were very kind to let us in and have a look around. So if you're ever anywhere near Orlando, kind of Florida, you should drop by and see this place.
And see Atlantis.
Oh, obviously that's the highlight.